welcome in this session. We are going to do an example on numerical differentiation. So here's a question. The table below shows values of a certain function. So we have x and then the corresponding values of x. So 1, 2.7, 183, 1.2, 3.9841, up to 2.6, whose value is 35.006. So the first question from this table is to draw a difference table up to the fifth difference. So draw a difference table up to the fifth difference. So this value at 2.2 is 19.855. This 19.855. So draw a difference table up to fifth difference. So this is how you draw the difference table. So you write one column x, so you list all the values of x from 1 to 2.6. And then the next column, you write the values of the corresponding, so the f values corresponding to these x values. And when you are writing these numbers, ensure that you leave spaces in between where the differences will be indicated. So the first column will be a first difference, second difference, third difference, fourth difference, and then fifth difference. The equation was to reach up to the fifth difference. Now, the way we get the difference is usually the lower number minus the upper number. So like for this case, to get 1.2685, it is this number minus this other number here. 3.9841 minus 2.7183. And then you use the same convention to find all the difference up to the fifth difference. Now, the aim of this question is to approximate the derivative of the function at the point x equals to 2.6. So x equals to 2.6 is this number here. So once you have identified the value of x, whose difference you want to calculate in the difference table, then you define a diagonal corresponding to that value and its value of f. So in this case, we'll be using this diagonal. So these are the values that we are going to use. Now, once we have identified that diagonal, next step is to now label those differences. And because the 2.6 is at the bottom or below the difference table, then we use the Newton backward difference formula. So this will be called backward, because the first difference will be first backward of Fn, this will be second backward of Fn, third backward of Fn, fourth backward of Fn, for this the fourth difference, and then this other one will be fifth backward of Fn. Some people use F naught throughout, there's no problem. Others can use the notation F naught throughout, or you can use Fn throughout. There's no problem provided you write the correct formula in the interpretation of these values. So always this is first difference, this column second, third difference, fourth difference, and then lastly, the fifth difference. Now let's go to the question. So the first question, B, the A was to draw the difference table. Approximate f prime of 2.6 using, so first one, 2 terms, using first 2 terms, and then number 2, 3 terms, number 3, 4 terms, and then number 4, first 5 terms. So that is the problem, to approximate that function using this number of terms, to get the derivative of the function using this number of terms. So step 1 is to write the general formula. So solution, we know that f prime of x naught is approximately given by 1 over h into first backward fn plus a half second backward of fn plus a third fn plus 1 over 4 fn plus 1 over 5 fn plus other terms. So remember I said other people you can use f naught throughout, provided you are interpreting it correctly in the difference table, there's no problem. So our first question, first 2 terms means you'll stop at this second backward difference. So therefore, you will say f prime at 2.6 is approximately, so h, the spacing between x values in this equation is 0.2. And then from that table, the first forward difference, the first backward difference is given by 8.5500 plus a half into 1.9490. And when you work out this one, you get 47.6225. Command 2, 3 terms means that our first derivative of 2.6 will be approximately equals to 1 over 0.2, 8.5500 plus 1 over 2, 1.9490 plus 1 over 3 into 0.42500. When you work out this one, the answer you should get 48.3308 3333. Number 3, first 4 terms implies that the derivative of 2.6 will be approximately 1 over 0.2 into 8.5500 plus a half into 1.9490 plus a third into 0.42500 plus 1 over 4 into 0.08900. And when you work out this one, your answer should be 48.4420 83333. And lastly, using first 5 terms, at the derivative at 2.6 will be approximately 1 over 0.2 8.5500 plus a half into 1.9490 plus a third into 0.42500 plus 1/4 into 0.08900 plus 1/5 into 0.016100. When you work out this computation, you should get the answer to be 48.4581833. That is how we answer that part. Question B, part B of that, part C of this same question. Given that f of x is x e raised to power x, find the absolute error and percentage error in B above. So to solve that one, we have to remember that absolute error is given by exact or true value minus approximate value. So the exact or the true value will be given by getting the derivative of this function and then replacing 2.6. So if f of x is given by this, then f prime, let this one to be u, this one to be v. So you differentiate by product rule. So u prime is 1, so times v will be e raised to power x plus v prime is the same, e raised to power x, so times u will have x e raised to power x, which will be 1 plus x e raised to power x. So which means that the exact value of the derivative at 2.6 will be 2.6 plus 1 e raised to power 2.6, which will be 3.6 e raised to power 2.6. So this is the true or exact value. So now we can easily calculate the errors at each of the points given in B. So Roman 1, when you use two terms, error, call it E1, will be true value, which is 3.6 e raised to power 2.6. You subtract our first value in 1 was 47.625. So this will give us 0.846956926, which means in this case, percentage error will be 0.846956926 divided by the exact value 3.6 e raised to power 2.6 times 100%. And when you work out this, you should get 1.747403375%. And then case 2, where we have 3 terms, let's call the absolute error E2 will be 3.6 e raised to power 2.6 minus the approximate value. In the case of 3 functions or 3 terms, we got our answer to be for 48.44208.333. The absolute value of this difference will give us 0. Actually, these are three terms. This was 48.33. Recurring. So we have 0.1386235596, which means percentage error 0.1386235596 divided by 3.6 e raised to power 2.6 times 100%. When you work out this, you get 0.28600,19583%. Now, comparing the error in the case of 2 terms, we had 0.84. 3 terms, we are getting 0.13. So you see the error is reducing. Similarly, percentage error for 2 terms was 1.7. Here is 0.2. So also the percentage error reduces. Now, for 4 terms, let's call the absolute error E3, epsilon 3. So it will be 3.6 e raised to power 2.6 minus our approximation. When we are using 4 terms, our answer was 48.44208333. Base difference and its absolute value is 0.0273. That's what we have, which is less than the previous one, which was 0.13. So this means percentage error will be 0.027373559601, dividing by the exact, which is 3.6 e raised to power 2.6 times 100%. Then that computation will give us 0.056647597011%. Also 0.05, and initially we had 0.28. So still the percentage error has reduced. Lastly, 5 terms. Absolute error, let it be epsilon 4. Exact is 3.6 e raised to power 2.6 minus approximate for this one was 48.4518333, and when you work out, you get 0.016236260.1. So which means percentage error will be 0.01762362601. We divide 3.6 e raised to power 2.6 times 100%, which on solving you get 0.03636027124%. You see, this is even less than the previous one. So from all these results, we can conclude that, in conclusion, the higher the number of terms, the lower the error, and the better the approximation. So when you use more terms, you are likely to get a more accurate answer than using less number of terms, as has been shown this problem. Thank you.